Hey everybody, Dr. G here with today's lesson on the quantum rigid rotor. So today we're going to learn about how quantum mechanics can affect the way things rotate. So let's get into it. So as we've learned throughout our course in quantum mechanics in physical chemistry, is that energy is fundamentally quantized. We can't get away from this. And, so the Hamiltonian for a quantum system is an expression for the operator that returns the total energy of the system when it operates on the wave function of the system. So that's what we have here, right? This h hat here. It operates on our time-independent wave function, right? Our spatial wave function, psi, little psi, operates on that, and psi comes out unscathed. It's just multiplied by a constant, which is its energy. And we can break down that Hamiltonian operator. In the next line, we see it separated into the kinetic energy operator and the potential energy operator, right? Because this is just the total of all the energy. So there's kinetic and potential. Here's kinetic. Here's a potential energy operator, right? So each one is labeled. And basically, so far, every system we've worked with uses this same approach of solving the Schrödinger equation, right? This is how we do most of the things we do in quantum chemistry in terms of trying to understand it, the theory behind what's going on, is by solving the Schrödinger equation. And so what changes from one system to the next, whether we're talking about a quantum harmonic oscillator, or the particle in a box, or hydrogen atom, etc., all these different things we've seen, the approach is the same, but something's changing, right? So what's changing is, how are we treating potential energy or kinetic energy based on how the system is constrained by its conditions? So let's expand on this notion that energy is fundamentally quantized. And so if energy is fundamentally quantized, then, the components of it must be quantized as well, right? So the separate kinetic and potential energy operators, they must also be quantized. And, kinetic energy, this T hat here, this is energy due to momentum, right? Any kind of momentum is this type of energy. So then if that is the only thing that can change and determine how much kinetic energy something has, well, then the motion must be quantized as well. Because, momentum, this is things in motion. So motion must be quantized. And then potential energy, right? So position, that's his energy due to position, right? So like for the quantum harmonic oscillator, how stretched or compressed is the spring, right? Looking at just a classical spring or a classical harmonic oscillator, the position of the harmonic oscillator tells you its potential energy. Is it at its equilibrium point, at its minimum, or is it stretched or compressed, and then that makes the potential energy go up. So that means that, so if we're looking at a quantum harmonic oscillator and potential energy is quantized, well, that's energy due to position, so position must also be quantized. So the quantization of energy leads to a quantization of both position and momentum as well. And so now, for the quantum particle in a 1D box, right, this was the first system we looked at. Did we need to concern ourselves with both terms of the Hamiltonian at all times, right? So, and when I say both terms, right, the kinetic contribution and the potential contribution to the total energy. Did we need to worry about them at all times? Well, sort of, right? Because we only cared about the potential energy in that the particle must be inside the box, right? So, because if it's inside the box, the potential energy function doesn't do anything. It just tries to keep it from leaving the box, right? So if it hits the wall, yes, it is an infinitely strong box, and it will not let that wall flex at all, right? It won't let the wall flex, and the particle is perfectly trapped inside of that box. So it can't tunnel out either, because for the example we did, we looked at an infinitely strong box, right? Our one-dimensional box. And how do we make an infinitely strong box? We set this potential energy function to be v of x equals infinity at x equals 0 and at x equals L, the length of the box. Now, of course, you can set that potential energy to some non-infinite amount, and then there's going to be some tunneling probability that you actually can see the particle in the wall, which would mean you have some non-zero probability of observing that particle inside of the wall of the box, even though it technically doesn't have enough energy to get through the wall, right? It's just because of this sort of fuzziness that comes with the question of where is something for a quantum system, right? That's how tunneling comes about. But anyway, my point being on this slide is that as far as solving the Schrödinger equation for the one-dimensional particle in a box, the potential energy function V really just kept us inside the box. But like the Hamiltonian inside of the box, we actually only looked at the kinetic energy operator T. And so the reason I'm bringing up the 1D particle in a box in a video describing the quantum rigid rotor is because I want to remind everyone that this model describes translational motion in a confined neutral space, right? So it's not interacting with, inside of the box, there's no sort of field or something like that that's pushing or pulling it anywhere, right? It's just, it's confined to a space and that's it. And the particle is only translating, so translational motion. Then later in the course, we looked at the quantum harmonic oscillator. And so let's ask that same question. Do we need to consider both terms at all times, to the kinetic energy operator and the potential energy operator? So for the quantum harmonic oscillator, did we need to care about both at all times? Yes, we did, right? Because fine, it's being confined in this way. We're in a harmonic well is another way of describing the quantum harmonic oscillator. And sure, it's in there, but anywhere, any position X has a different potential energy value, right? I mean, it's symmetric, right? If you compress or extend the spring beyond its equilibrium point to the same amount, you're going to get the same potential energy on either side of stretching and compressing it. But you know what I mean, right? That basically the way the position affects the potential energy, that does not go away, right? It's not like once we're in the box, we can kind of forget about it like we did for the 1D quantum particle in a box. So this one, we had to care about both at all times. So the quantum harmonic oscillator describes a vibrational motion for a quantum mechanical object. And the reason I bring this up during this video is because this is another type of motion that a molecule can undergo, right? So we talked about translation, right? You can imagine a molecule moving along a straight line, right? If you throw a molecule across the room, right? That's translational motion. Whereas vibrational motion, right? That's where the molecule vibrates. So that's another type of molecular motion. So far we've covered two types of molecular motions. And now that brings me to the next question. So do you think that energy due to angular momentum, i.e. rotational motion, do you think this is also quantized? So think about that for a second. Maybe pause the video. And yeah, you bet it is. Rotational motion, right? That causes an angular momentum. That's energy, right? There's energy associated with that, right? If you think of like a flywheel or something like that, right? For an engineering application, a flywheel is a rotating mass that stores energy, right? So absolutely, there's energy in a rotating mass. And if it's a quantum mechanical rotating mass, then yeah, that energy needs to be quantized. So does this mean that there are only certain observable rotations for molecules, right? Can a molecule just rotate freely, or are there only certain observable ones? What do you think about that? Yes again. So, a molecule can't just rotate any which way it wants, just as you saw with, like, say, for example, the particle in the box, right? Remember, there were nodes in the wave function, which led to nodes in the probability density function of where you could observe the particle. So there are positions that you will never, ever see for a quantum mechanical system where it's translating and you're measuring where it is, right? The same thing with the rotational states for quantum systems, right? There's certain ones you can see. Some are very likely, some are impossible, some are very not likely, right? So there are, a molecule can't just rotate any which way it wants. The rules of quantum mechanics do apply here. So now, before we introduce all the quantum effects that can happen with angular momentum, let's first carefully define it in a classical sense and build up from there. So, standard momentum, right? Translational momentum. We call that P equals mv. So momentum is P and mass times velocity. That'll give you your standard momentum, right? Moving along in a straight line. But angular momentum is defined as J equals I omega. And this A, notice there's an A subscript. So that indicates the axis of rotation, because you could say, okay, something's spinning, but along what axis is it spinning, right? So the guy in the chair is spinning around. We're calling that straight up and down axis A, right? But what if we stopped it and this guy started doing backflips, right? That would be a different axis of rotation for the guy in the video here. And so this is why, you can't just define an angular momentum in general for an object. You say, well, which axis is it rotating about, right? So that's an important piece to it. Okay, so now what do we mean by the I and the omega here? So I is the moment of inertia, and the moment of inertia is defined below, right? You take the sum of each of the masses that are in the system multiplied by their distance squared, and then the distance from what? The distance from the axis of rotation that you're looking at, right? So if we look at these dumbbells the guy's holding, how far are the dumbbells from that axis A? That's the distance we're talking about. So you multiply each mass in the system by its distance squared, you sum all that together, and that is your moment of inertia. That's all there is to it. And then omega is the angular velocity, right? So that's like in units of inverse time, right? So you could be like radians per second, right? But it turns out radians is actually unitless, right? And this is because radians is a ratio of lengths, right? There's the arc length and there's the radius length, right? And then this is where radians comes from, right? Because pi is a ratio of circumference divided by diameter, right? Those are two lengths. So if you divide those, you end up with a unitless quantity. And so radians is basically how far around the circle have you gone? Well, that is unitless. So the units for omega are just inverse time, right? How far is the angle gone per second or per microsecond, whatever your units are for time. So now let's look at a structure that looks a little bit more like a molecule here, right? So again, the same principle applies for calculating the moment of inertia for a given axis, right? So we have an axis labeled there as A, right? Going up through those, right through the center there, right? And so if we choose that, then we can figure out all those distances from all the masses to that axis, right? So I just wanted to kind of share this visual here of what this would mean for a set of masses like in a molecule, right? These could all be nuclei of different atoms that are part of the same molecule. So, the subject of this video, the quantum rigid rotor, what is it? Well, you can think of a quantum rigid rotor as the toy model that describes pure rotational motion in a quantum system here, right? So first we had translational motion with the particle in a box. Then we had vibrational motion with our quantum harmonic oscillator. And then now we're talking about rotational motion with the quantum rigid rotor. And that image on the right, basically, I'm teasing what's coming after this class is we're talking about rotational spectroscopy, also known as microwave spectroscopy, where you can actually observe transitions between these different allowed rotational states for some molecules. All right, so if we're really going to do the quantum rigid rotor, we need to solve the Schrödinger equation, right? This is how we get all the things we're doing here. So let's return to our good friend, the time-independent Schrödinger equation. So there it is, as it always is. And so for a quantum rigid rotor rotating in isolation, what is the potential energy function? And I hinted at this at the beginning of the video, right? Well, do we care about this? Do we care about that? Right? When I was talking about that, what do you think? Well, if we must write one, it's just V of x equals 0, right? Because basically, this is just a rigid rotor. It's rotating in space. We're not saying that there's some field modulating it in some way. It's just a freely rotating rotor, right? A quantum rigid rotor. So yeah, we actually don't need to care about the potential energy if we're only looking at a rigid rotor like this. So we've dropped the potential energy term from our Schrödinger equation, but now let's look at our variables. So we're looking, right now we have our one-dimensional Schrödinger equation in the dimension x. So is it possible to describe rotation in a single spatial dimension x? So think about that. Is it possible? Can I do that? Nope, you cannot do this, right? You can't rotate something in one dimension, right? Because maybe you could argue you're rotating a point, but by definition, you can't rotate a point, right? That's not how points work, right? They don't actually occupy any volume. So anyway, yeah, so imagine trying to rotate along a single axis. It's impossible to do. We need this model to occupy 3 dimensions. And although it's possible to do with x, y, and z coordinates, our standard Cartesian, it actually makes much more sense to use our spherical coordinates, r, theta, and phi. And you might be thinking, you could describe rotation in 2 dimensions, and you could do this, but ultimately, we want to consider molecules that exist in 3 dimensions. So we're going to go straight to 3. Well, we've already seen a Hamiltonian operator in spherical coordinates, right? That's what we had to do for the Schrödinger equation for the hydrogen atom. So we're going to return to that. So at the top of the screen now, that's all that is. We've seen this before. This is the Schrödinger equation for the hydrogen atom in spherical coordinates. And we just determined we do not need the potential energy. So we can just drop the potential energy term from that. And this is going to be our Hamiltonian operator for this system. So here is our Hamiltonian operator. And if we, plug our Hamiltonian operator into the Schrödinger equation, it looks like this. So there it is, operating on little psi to get little psi out multiplied by its eigenenergy E. So if you recall the Laplacian operator, right, that triangle squared looking thing, right, that the name of that is nabla, right, the Greek letter nabla. So nabla squared, that's our Laplacian. And you might remember that all 3 degrees of freedom appear in that. There's r, theta, and phi. And so what can we say about r for a rigid rotor? So just think of like 2 masses, right? Like a dumbbell looking thing, right? Where you have 2 masses rotating about their center of mass, right? So what can we say about r for that if we define it as a rigid rotor? Well, little r is actually a constant, right? We said it's rigid, right? If that's rigid, then the distance between those 2 masses will not change. So little r is actually not a variable, it's a constant. So instead of little r, we can plug big R in, which will just say that is the distance between the masses that our system is fixed at, and we can plug that in. So that's going to be what we do on this next slide. But before we get to that, let's look at the reduced mass real quick as well, because reduced mass, well, that's the definition of it right there with mu. But reduced mass also shows up in our definition for the moment of inertia, I. So I equals mu r squared, where r is the distance between the masses, which of course we've said we've fixed that at capital R. So we can plug that in. So now that coefficient in front, we're going to write it as minus h bar squared, big R squared over 2I. So that's changed there. And so now let's see if we can even go a step further, knowing that our variable little r has been replaced by a constant big R. So let's look at that Laplacian. So here's the full Laplacian in spherical coordinates. And notice we have a partial derivative with respect to little r. Well, a derivative with respect to a constant, right? Because that little r is now big R, it's constant. What do we know? Well, that's going to go away, right? We can simplify the Laplacian because it has a ddr in it, and that's just going to produce a 0 anyway, so we can get rid of it. And so that's what we do here. And then also notice there's that little r squared, that 1 over little r squared. Don't forget that that's there too, right? So that 1 over little r squared becomes 1 over big R squared. And so now our rigid rotor's Laplacian has become simplified for us. So this is great. And we can simplify that a little bit further, right? So we went from this definition of the Laplacian on the bottom left and our Schrödinger equation on the bottom right. And so now we can write it in this way, where all we've done is shown that big R squared is going to cancel out. So now we have it. We have a Schrödinger equation for the quantum rigid rotor, right? Remember, in quantum mechanics, just setting up the Schrödinger equation that needs to get solved is a step in and of itself. You have to figure out how to set it up before you can try to solve it in some way. So now, what are the energy levels for this thing, right? If we have the Schrödinger equation, that's great, but maybe we can come up with a way to figure out what the energy levels are, right? So maybe not worrying about solving it to actually find out the form of the wave function little psi that's going to make this statement true. Let's just kind of take what we know about solving the Schrödinger equation and just figure out the pattern for the energy levels for now. Well, as we mentioned that, we're building off of our solution from the hydrogen atom that we already had. And so looking at that solution at the bottom there, right? This is the pattern that the solutions to the angular portion of the hydrogen atom follow. So remember, we used separability, right? We separated the problem of solving the Schrödinger equation for the hydrogen atom. We separated it into a radial component and an angular component. And those were basically 2 separate Schrödinger equations that we could solve separately to produce separate families of solutions. Right, so you have your radial wave functions and your angular wave functions, and then we later combined them. So just looking at the angular piece, that's what we have at the bottom here. And we remembered that it followed this pattern of minus L times L plus 1. right? So these eigenvalues that are energies, they follow this pattern. So now looking at these two, let's compare the two. I mean, these equations are so similar. What could I do to the bottom one to make it the same as the top one? So take a moment to think about that. And we see that, yeah, you can multiply both sides by minus h bar squared over 2i. That's all we have to do. And then they're the same thing. Well, that's all we have to do then to get an expression for the energy for a quantum rigid rotor. So we've got it. We have an expression for the energy of a quantum rigid rotor. Here it is, where basically we have a letter J that we use instead of L, just to save confusion, right? So we switch that to a J just to kind of remind everyone that we're talking about a quantum rigid rotor here. But that's still an integer, right? J can be 0, 1, 2, 3, 4, whatever integer you want is allowed there. And then we have h bar squared over 2i, where I is the moment of inertia. So notice something very important. Although we derive this using a simplest rigid rotor, right? Just two masses coupled together, rotating about their center of mass. Notice that this expression only includes J, I, and H bar, right? So basically, if we can calculate a rotational moment of inertia, or moment of inertia I, about some axis, we're good to go, right? We're not limited to one type of rotor. We're not limited to the simplest rotor. Now, granted, we have to treat them differently, and don't forget, you can rotate along 3 different axes, right? If you're in a 3-dimensional space, there's 3 different axes that you can rotate about. But nonetheless, like the fundamental thing is here. So why should a chemist be so excited about this? Well, we can treat molecules as comprising a collection of masses that are rigidly coupled together. Right? So we could say that molecules, all right, we're going to treat them as rigid rotors. Now, this is making an approximation. We're approximating bonds as being rigid, but right now we're just trying to understand the way they rotate, right? So this is how we build models, just like in the ideal gas, where, just the PV equals nRT type ideal gas, right? The particles, they pass right through each other, right? They don't take up any space. They're not attracted to each other. But nonetheless, it's a very useful approximation that you can use to solve lots of stuff. Similar thing here. We're going to say, all right, for what we're trying to understand right now, our molecules are rigid. All right, so this shows in more detail these different rotational axes and the different sort of shapes, basic shapes that we see in rigid rotors in the context of studying molecules and how molecules have rotational motion. So notice that we have 3 orthogonal axes for all 4 of these examples here. And basically, if you want to imagine like how these things rotate, just imagine that you're grabbing one of these axes between your fingers and you basically spin it around. And you make it rotate. So if you can apply a twisting motion along each of these 3 axes, imagine if you wanted to sort of reverse the direction, right? You twist it one way, then twist it the other. How much would the molecule fight you going from one way to the other, right? And that can give you an idea of what's going on with rotational inertia along the 3 different axes. So once again, just to remind you, we solved the Schrödinger equation for a linear rotor with just 2 masses, but we can generalize that solution to these different values of I, our rotational moment of inertia, depending on the structure of the rotor that we're referring to. First, let's just define geometrically, classically, what are we talking about here, right? So let's take a little break from quantum mechanics, and let's talk about how are we defining these axes. Well, so there's always 3 perpendicular axes of rotation, and you can actually consider this, it is a basis set of all possible rotations. So any way that you can imagine any of these structures on the screen tumbling through space, it's going to be some linear combination of the 3 possible rotations that it can do. So similar to the way we talked about the Cartesian unit vectors, right? X hat, Y hat, and Z hat. Remember, we can define any point in space as just a sum of those 3 vectors, each one multiplied by some coefficient. It's the same thing here with rotations, right? So it's not just for position, you can do it for rotations. So again, we have a basis set here. And the convention, the way you define the rotational axes here is typically done where you go by the magnitude of the moment of inertia, right? So C should be the largest, followed by B, and then A should be the smallest moment of inertia. Now we return to the linear rotor. And interestingly, due to symmetry, some of these rotors are actually going to have fewer than 3 unique values for I. So, we have these rotations we can talk about in this basis set of IA, IB, and IC, but some of them are not necessarily going to be unique. And in fact, for the linear rotor, one of them is undefined. So if you look at the linear rotor, we have I for both of them, because whether you, again, imagine that you're grabbing the axis between 2 fingers and you twist it, right? If you do that, basically it's going to feel the same to you for either of those values of I in that image, right? You're just going to rotate the same rotor. You just grab one or the other. It's the momentum, right? As you twist it and you rotate and you reverse directions, it's going to feel the same. It's the same. But notice rotating it around the one labeled 0. If you grab that and spin that one, you would actually get no resistance to reversing the direction. And the reason for this is because the nuclei here, right, we're treating them as points. You can't rotate a point, as we talked about. So basically, that's why that one is 0. That one's not defined. So there's actually only 2 defined rotations for the linear rotor, and their magnitude's going to be the same. Now looking at the spherical rotor, that one has 3 moments of inertia, right? You can have a legal rotation about any of the 3 axes, but the magnitude is actually going to be the same for all 3. And the symmetric. So for the symmetric, what we mean by symmetric is that basically there's going to be 2 rotations that are equivalent, right? So if you look at the ones that are labeled I perpendicular, right? That symbol that looks like an upside down T means perpendicular. So if you grab either one of those and spin it, it's going to feel the same to you. But if you grab the top one between your 2 fingers, that's going to feel different, right? That's parallel. Those 2 lines together means parallel. So that is along that axis, which is actually for this type of rotor is often called a principal axis. The unique one is the principal axis. If you twist along that one, that's going to feel different from the other 2. And finally, we have the asymmetric rotor, where basically these are molecules where there's no symmetry to be had here. Each rotational moment of inertia for this one is unique. So maybe this one bothered you a little bit, right? When I said that, this tetrahedral rotor here, this is spherical. And looking at that, it kind of bothered me a little bit when I saw it in the book when I was preparing this lecture. And I thought about it, and that representation is actually not quite right? So they have this pyramid-looking structure, right? This is a triangular-based pyramid, not a square-based pyramid like you would see in Giza, right? This one has a triangle at the bottom. And these axes of rotation are actually not correct. If you spun those 3 different axes, they would actually feel different to you. They would not feel the same. So it's not that this is not actually a spherical rotor. It is actually a spherical rotor. It's just that image is deceptive. It's not quite right. So instead, imagine that there's a sphere surrounding a rotor like the one in the image there. So I put a blue sphere around that rotor. And imagine that sphere is sized so that each of the atoms in the outer part, right? Because rotations about a single atom don't count, right? Because that's a point. So the one in the very center there, that contributes nothing to the rotational inertia here. But the ones on the outside, right? They're all just touching the sphere at a single point, right? So they intersect with a single point. And now imagine you measure the distance, the arc distance between any of these points and their nearest point, right? Their nearest atom here along that arc distance. Are they already as far apart as they could be from each other, or could you possibly move them a little further apart? Think about that for a second. Try and visualize this. And yeah, they are. They're already as far apart as they can go, right? If you learn like that, the Vesper theory stuff in organic, right? This should maybe remind you of that. They're as far apart as they can get. So this means that the mass distribution on that sphere is already in perfect balance. So yeah, this is considered a spherical rotor. So these 2 images on the screen are truly spherical rotors. It's just that the way that pyramid-looking structure on the screen, don't look at that. That's not correct the way it's labeled. Instead, it should be oriented like this. So here we're seeing a methane molecule that, if you look at the one at the top right and the one that I have rotating in the center of the screen there in the bright green, that's the same molecule. They're both methane. I've just oriented it differently. And if it's oriented in this way, you can see that actually these rotations about IA, IB, or IC actually are equivalent now. They're no different, right? So the magnitude of the angular momentum, if this thing were rotating at the same frequency at any of these axes, would be the same. So this is actually the way that this particular molecule should be oriented, to show you that it really does have spherical symmetry from the perspective of a rigid rotor. All right, so returning to our goal of talking about kinetic energy in terms of angular momentum, let's start looking at these rotors in this three-dimensional space where they actually live here. An expression for the kinetic energy due to rotation of a rigid rotor, if we write that in terms of classical energy, right? This is what it would be. We have a sum where each term in the sum is just basically along these three axes, A, B, and C. And of course, omega is our angular velocity. How fast is it rotating? So you might remember that back when we were doing the one-dimensional particle in a box, and I was talking about the kinetic energy term, and you notice that in the Schrödinger equation, kinetic energy doesn't really look like 1/2 mv squared, right? It has momentum instead of velocity, and so we converted it back then, and we're doing the same thing now. So each one of these terms, we can multiply it by I over I, right? Because that's just one. You can multiply things by one wherever you want, right? That's always allowed. And so if I multiply the IA omega A squared by IA over IA, then I can actually write JA squared over 2IA, right? So that's like the first term of this energy expression here. But all I did to go from the top equation to the bottom one is multiply each term by I over I, where we make sure that it's the same axis that we're looking at, right? A, B, or C. Okay, now we're ready to get back into the quantum mechanics. So we've defined classically what it means to have kinetic energy due to rotation and sort of our convention for that. And so now let's bring the quantum mechanics back in. So again, here's that expression for the energy levels for a quantum rigid rotor. And if we relate that to this expression we just wrote down at the bottom of the previous screen for energy, our goal now is to connect these two things. So first, let's think about the units before we go any further. So looking at this expression, I just did something simple. I just distributed that 1j in. So we have j squared plus j. So if I have some quantity that I'm adding together and one is squared and the other is not, j squared plus j, what does this tell you about the units of j? It doesn't have any, right? That's what it tells you. Because if let's say it was in meters, and I was adding square meters to meters. That's crazy. You can't do that, right? You can't add an area to a length. It's meaningless. So therefore, we know J has to be unitless. And, I think we already knew this, but it's good to kind of prove this to ourselves as we go through this proof. And so then that means that all of the units are coming from h bar squared over 2I. Well, h bar is in units of energy times time. And so energy is a derived unit, right? It comes from mass times length squared over time squared. And then you multiply that by time, and we're left with mass times length squared over time. Okay, so now let's look at our J equals I omega. So J equals I omega, right? This was our classical expression for angular momentum. And we see that that is mass times length squared times 1 over time, right? The 1 over time is for the omega. And this, of course, simplifies as well to mass times length squared over time. So great. This means that the classical j squared and the quantum constant of h bar squared are in the same units. So therefore, we can plug j times j plus 1 times h bar squared right into our classical expression for j squared. And let's think a little more carefully what j squared actually is, right? Because the momentum of a rotor, the angular momentum of a rotor, is actually a vector. So that angular momentum vector J actually has 3 elements. It has JA, JB, and JC, right? These rotations about the different axes. So then if we want to do, J squared, what is that really? You're really taking the dot product of the vector with itself. And the definition of the magnitude of a vector, that's at the very top there, right? See, I have the magnitude of a vector v is just v dot v, and then you take the square root of that, right? Because v dot v gives you a constant. That gives you a scalar. You take the square root of that, and then you know the magnitude. So therefore, j dot j, or j squared, that is actually the square of the magnitude of the angular momentum. So all the angular momentum, right? Not looking at one particular component, right? We're saying if we take that entire vector of angular momentum and you take the dot product of it with itself, that is the square of its magnitude. And so that's what we see here. Right? So that's how we get this expression, right? We've been saying that, looking along a single component, you say, okay, yeah, JA squared over 2IA, right? But now we're looking at the whole thing together, right? So that's why we have this little like fancy J that we call like a curly J. So that curly J squared is actually the square of the magnitude of the angular momentum. And so, why can we just divide the square of the magnitude divided by 2I and not really specify, which axis and all that stuff? Well, we were able to combine them. Right, so that expression on the right, that E equals, the 3J's squared altogether over 2I, right? The reason why we're doing that is because we're taking advantage of the fact that this is a spherical rotor. Because normally this would have been, JA squared over 2IA squared, over each one would be over its particular moment of inertia I, right? IA, IB, or IC. But as we pointed out on the previous slide, the magnitude of I for A, B, and C for a spherical rotor is equivalent. Right, it's the same magnitude. So therefore, we could just combine them like this, and we get this really nice compact way of writing it, where we have this little fancy J squared over 2I, or sometimes we call that a curly J. And so the curly J is the magnitude of the angular momentum for a spherical rotor here. And of course, on the previous slide, we showed that the units are the same, and therefore we can express this directly. So we've shown that this expression here, this curly J squared over 2I, we can actually take our quantum expression, J times J plus 1 H bar squared, and replace the curly J squared with that, and we've produced an expression for the rotational energy levels of the spherical rotor. There we have it, equation 12b.6. So that was the energy levels, and it's often convenient to express the energies in terms of wave number. And why is that? Because as I mentioned, this relates to spectroscopy, in particular, microwave spectroscopy or rotational spectroscopy is what ties into this. And wave numbers are a lot easier to look at in terms of your measurements and things like that. You don't directly measure energies, you're measuring wavelengths, which you convert to a wave number very easily. So that's the purpose of the equations here, is just taking this expression for energy and converting it into an expression in terms of wave number instead. So, make sure you pause the video and work through these steps as well in your head and sort of convince yourself that this is all correct. All right, so now that we've explained the spherical quantum rotor, let's look at the symmetric one. And so this one's a little more complicated because now these axes of rotation, they're not all equivalent. Two of them are, right? At least the magnitude of I is not going to be the same for all of them, right? If we look at the perpendicular ones, there's two ways to rotate perpendicularly, but there's one principal axis as well. And you can look at the image on the left where we have this hexagonal-based prism, right, where you can rotate it along the perpendicular axes and it feels the same, or you can rotate it along the parallel axis, right, I parallel, and it's different. So there's one unique rotation and two non-unique ones, right? The I value is going to be the same for two of the axes and different for one of them. And the one that's unique, we refer to that for this particular rotor, right? The symmetric rotor, we call that the principal axis. So the unique axis is the principal axis. So up next, let's figure out an expression for the energy levels for the symmetric rotor, because it's going to be different, right? There's that one axis is different from the other two. So step one, let's take our normal energy expression here, right? This J squared over 2I, right? Where we just have the three axes treated separately. And then we make a substitution. We just say, okay, the principal axis is A. Right? By convention, we use A as the principal axis here, and then B and C, we're going to make those both each one of the perpendicular ones. So let's substitute that in. And then once we make that substitution, now we can gather some terms together that can go together, right? So the last two terms have the same denominator, so we combine them. And if we look at that, so look at this expression here, and then look at our definition of curly j squared. So it's only missing the parallel, right? So that's this numerator here is only missing that. So if we subtract that from this, we can replace that, right? And that's what we do. So we replace this that expression with curly j squared minus j parallel squared. So we've now managed to incorporate the total magnitude of the angular momentum squared into our expression here. So let's keep going. Now, at this point, we make another observation. We say, well, let's split these things back apart because, again, we have the same denominator for these two things. We'll split them back apart, and we will remind ourselves that, wait a minute, we know how to bring the quantum mechanics into this. Once you have incorporated the magnitude of your angular momentum into the expression, now we can make that quantum substitution because we have an expression for that. So now we plug that in, and now our equation has incorporated some quantum mechanics. But we're not quite done yet. So because this thing is not fully quantized yet, right? The first term is quantized, the second two are not. So we're not done. And if we look at that, well, we could factor out this j parallel. So we'll factor out the j parallel, and now we have this expression. Now bringing that last expression back up to the top because we're out of room, we put that there. And the first thing we can do is let's just kind of simplify some constants here, right? Let's define a constant b that's just h bar squared over 2I perpendicular. So if we define b this way, we can bring that outside, and then we have b times j plus 1. And then that second term on the right, we left it alone. And now looking at that, well, okay, here's what's left there. Well, we have a 1 over I omega perpendicular. Well, we just defined something. We just defined b that was h bar squared over 2I omega perpendicular, right? And we've already got the 2 there, so what we can do is we can just call that b over h bar squared now. So that's the substitution we made. We're just using this thing b that we just defined, this constant b. We're substituting that in to further simplify things. Next, let's define a new one. Let's define something called a. So we have a b, why not have an a too, right? So we're going to call the other one a. And for this one, it's going to be just like b, but instead of I perpendicular, it's going to be I parallel. So with that, now we have a over h bar squared minus b over h bar squared inside of those parentheses. So we might as well pull out the h bar squared because that's in both. We pull out the h bar squared. This thing's starting to look nice, right? So we're at this point now. And, we're still not quantized. That second term is still not quantized, so we have to fix that. But we know that energy due to angular momentum has to be quantized. We've already figured this out. It's energy. Energy is always quantized. So it's got to be some multiple of h bar. So because that's some multiple of h bar, we're going to substitute in, instead of j parallel squared, we're going to call that k h bar, right? So instead of j parallel, it's k h bar. And so we substitute that in where basically k is an integer. So this is an integer multiple of h bar is what this is. And that whole thing is squared. Well, the way squaring things work with the parentheses like that, right? Both things get squared. Both k and the h bar get squared. So then our h bar squared cancels out and we've got k squared. And now we have a fully quantized expression. So this is very interesting because we actually have two quantum numbers now. We've got j and we've got k squared. These are our two quantum numbers here. So here is our expression for the energy levels for the symmetric quantum rigid rotor. And so of course, here's our expression. We have our quantum numbers j and k, and we've got our values of b and a defined. But is there a constraint between k and j? Yes, there is. Yes, there is a constraint here. And it's actually very interesting. So, okay, so j can be 0, 1, 2, etc., anything you want. K can be 0, or it can be, plus or minus 1, plus or minus 2, ranging all the way up to plus or minus j. So let's say we have j is 2. Well, if j is 2, then k can be -2, -1, 0, 1, or 2. Those are the only allowed values for k, to give an example. So what does this mean? Well, when k equals 0, that means that there's no component of angular momentum about the principal axis. The energy is only dependent on I perpendicular. So that's basically saying if this is the case, that k is 0, all of the rotation is due to the perpendicular rotations. Another important interpretation to get out of this is that, the sign of k doesn't matter. Notice that k is squared. So whether k is -1 or +1, -2, positive, it doesn't matter. And it shouldn't matter, right? If you imagine you have a flywheel, right? You're spinning some big wheel, some big heavy wheel, and you get it spinning. It has some sort of kinetic energy due to rotation. Does it matter whether you spun it clockwise or counterclockwise? No, it doesn't matter. That won't change the total kinetic energy of the system. And finally, when k equals plus or minus j, in that case, so let's say like j equals 2 and then k equals 2 as well, right? This type of scenario. In that case, then almost all the angular momentum arises from rotation about the principal axis, and the energy levels are determined largely by I parallel along that principal axis. So this is interesting because notice that the symmetric rigid rotor can have all of its energy partitioned into the perpendicular axis of rotation. That's allowed, but not the parallel. So you can't say that it's only rotating about the principal axis. So that's weird, right? Like when you see this should sort of jump out at you like, hang on, why is that not allowed? And you might think, okay, maybe there's something wrong with the model, but maybe it's something else. In fact, maybe it is some weird quantum effect going on here. And yeah, it sure is some weird quantum effect. It's one of the most famous ones. It's the Heisenberg uncertainty principle. So how is the Heisenberg uncertainty principle not allowing us to have the molecule only rotating in the principal axis? Well, okay, I'm just going to read this exactly because I worded this very carefully. So by definition, the rigid rotor comprises a set of masses at fixed distances from each other, right? We defined that from the beginning. We said this is a rigid rotor. Nothing's vibrating. They are locked in place. So their relative positions are not moving. So if we could make 100% of the magnitude of the rigid rotor's angular momentum due to rotation about a single axis, a single unique axis here, right? The principal axis. So we said that, okay, all of the rotational motion happening is along the principal axis, and that accounts for 100% of the magnitude of the angular momentum. If that were true, well then we would have to know exactly the angular momentum, right? Because that's only one axis. We know exactly what the angular momentum is along that axis. We also know the positions of the masses, right? If you think about this, if this rotor is perfectly rigid, the positions of the masses relative to that axis of rotation, right, they would not change at all if they're rotating about this single axis. So therefore, Heisenberg forbids us from exactly knowing both of these quantities, right? You can't know the position of the momentum to exact precision, right? You can't know that perfectly. So if it were allowed to only rotate along this single unique principal axis, if that were possible, it would violate the Heisenberg uncertainty principle. And I think that's fascinating. So now, okay, why is it allowed to be confined to only the perpendicular one? Well, there's two of them, right? We don't know in that term of our expression for energy, it doesn't say which axis. It doesn't say which perpendicular axis. In fact, these two perpendicular axes of rotation that we're defining here, they're indistinguishable. There's no way to know which one is which. So that's why you're allowed to have the rotation to be confined only to those two axes, because you don't know which one it is. So you don't have all the information because you can't have all the information. Heisenberg won't let us. So that's why it can be all in the perpendicular rotations, but it can't be all in the parallel rotation, is because there's only one. So there's only that one principal axis, so it can't be all there. And I think that this is fascinating, that it comes back to the Heisenberg uncertainty principle. And that just emerged from the mathematics, right? We didn't put that in there. It just came out of it. So to give you context now, the quantum rigid rotor is the toy model that describes pure rotational motion in a quantum system, right? Molecules are not actually rigid, right? They vibrate and they translate. They have these other ways of having kinetic energy, right? Vibrations include kinetic energy, translations include kinetic energy, and rotations include kinetic energy. There are these different things, and it's not like, we can tell the molecule to only do one of these things. So in reality, they're doing all these things. But this is a really useful toy model to say, like, all right, I just want to understand rotation right now. And then that's what we're doing. But in reality, in experiments and things like that, often we talk about rovibrational states. So this is both rotations and vibrations, and they're coupled together. We're not saying like, oh, these are separate. No, they're coupled together. So you can imagine that if you have a rotor, like say this carbon dioxide molecule is spinning around really fast, it's rotating quickly. Do you think that would affect the way it vibrates? Yeah, it would. Right, the vibrational states, it might actually prefer some higher energy vibrational states because of centripetal forces, right? Because it's rotating. So these things are actually tied together. Another thing that's really cool, rotational, or also known as microwave spectroscopy. You can actually measure these changes in the rotational states, and it's typically done on gases because basically, we're trying to observe rotations. Well, if the molecules aren't free to rotate, right? As I said, the molecules do whatever they want. They don't care about you, right? The molecules do whatever they want to do. So if the thing we want to see is rotations, well, we got to spread them out, and that's a gas, right? So this is typically gas phase measurements that we can actually see these transitions between these allowed rotations and these disallowed rotations, or forbidden rotations. So they're not all allowed, right? As we keep seeing with quantum systems, you see certain things you're able to observe and other things you just can't. The molecule's never going to do that. Right? Just as how in the particle in a box, there are certain positions you can never observe the position. It'll never be there, right? Because there is a node in the wave function which then produces a zero value in the probability density function, right? There's certain positions you'll never observe. You can't. Same thing with these rotations. There's certain rotations that you would never observe. You'll never see them. And I just think that is so cool to think about. So thank you so much for watching. If you like, subscribe, and share these videos, it'll definitely help other people find out about them, which would be great. Thank you so much for watching. I hope you enjoyed this video on the quantum rigid rotor. I'm Dr. G, and I'll see you in the next video.